Take a good look at this machine, the Hermel C42 UMT. The Hermel C42 UMT is a 5-axis machining and turning center made in Germany. And yes, it's as impressive as it sounds. What makes this machine special is its ability to both mill and turn a workpiece in a single setup. That means less time moving parts from machine to machine, fewer chances for error, and tighter tolerances all around. The machine features a trunnion-style rotary tilt table that can rotate 360 degrees and tilt from +30 to -110 degrees, giving operators full access to nearly every surface of a part without ever flipping it over. It handles workpieces weighing up to 300 kilograms, that's about 660 pounds, and holds a maximum turning diameter of 630 millimeters. The spindle on this unit runs up to 18,000 RPM with HSK A63 tooling, and the turning spindle delivers up to 700 Newton-meters of torque. For hard metals like titanium, Inconel, and hardened steel, that kind of torque makes all the difference. What you're watching right now is the machine running a complex aerospace-style component, cutting, turning, and finishing in one continuous cycle. The control system uses Heidenhain TNC 640, one of the most trusted CNCs in precision manufacturing. Now, let's step inside one of China's most impressive steel manufacturing operations, Shandong Ireda. These folks don't just make steel balls. They make millions of them, with extraordinary precision. The process starts with high-carbon steel rods fed into a rolling mill at temperatures exceeding 1000 degrees C, hot enough to glow bright orange. As the rod passes through precisely angled skew rollers, it's shaped and cut simultaneously into perfect spheres. No welding, no casting. Just raw steel, heat, and mechanical genius. Each ball then enters a hardening line, quenched rapidly in water to lock in surface hardness, sometimes reaching 60 to 65 HRC. That's harder than most tool steel you'll find in a workshop. These grinding balls end up inside massive ball mills at mining and cement plants worldwide, pulverizing ore and limestone day after day without breaking a sweat. Simple concept. If you've never seen a plate rolling machine handle steel that's 120 millimeters thick, get ready, because this is the kind of thing that makes engineers smile and everyone else's jaw drop. The machine in this clip is a Faxon heavy-duty 4-roll plate bending machine, an Italian-engineered marvel built for extreme industrial work. Faxon has been crafting these rolling machines since 1954, and their reputation in heavy fabrication is rock solid. Before the bend begins, operators carefully program the roll positions using the CNC control panel, calculating the exact pressure needed to curve steel this thick without cracking or spring back. The top roll drives the plate forward, while the two side rolls apply forming pressure from below. The fourth roll locks the trailing edge, giving operators full control throughout the entire bend. As the machine engages, you can actually feel the power. Thousands of tons of force shaping steel the way a craftsman shapes clay. The plate moves slowly, deliberately, because at 120 millimeters, there's absolutely no room for error. The result? A perfectly curved steel shell ready for pressure vessels, wind tower segments, or heavy industrial cylinders, structures that will stand for decades. Old-school Italian craftsmanship, modern engineering power, a combination that never gets old. You know, humans have been shaping hot metal with hammers since the Bronze Age, and today, we're still doing it. We've just gotten a whole lot better at it. What you're watching right now is called radial forging, and if you've never heard of it before, don't worry. By the end of this clip, you're going to understand exactly why the biggest companies in aerospace, defense, and automotive manufacturing depend on this process every single day. So here's the idea. Radial forging is a high-productivity forging method specifically designed to shape metal parts that have a long, extended axis. Think shafts, tubes, rods, gun barrels, steering columns. Instead of hammering straight down like your grandfather's blacksmith, The Radial forging machine uses 4 precision hammers, arranged in a cross pattern around the workpiece, and they strike simultaneously from all 4 sides at once in rapid synchronized blows. That's the radial part. The force doesn't come from one direction, it radiates inward from all angles at the same time. Now the machine you're looking at is no ordinary press. These radial forging systems, like those built by companies such as GFM in Austria, can deliver hammering frequencies of up to 900 strokes per minute, with forging forces exceeding 500 tons. The workpiece is fed through the machine on a precisely controlled chuck, rotating and advancing in tiny, exact increments with each hammer blow. The result? A perfectly shaped part, with incredibly tight tolerances. What makes radial forging really special, and this is the part engineers love, is what happens inside the metal itself. As the hammers compress the workpiece from all sides, the internal grain structure of the steel is refined and aligned along the length of the part. That's called grain flow refinement, and it dramatically improves the fatigue strength and toughness of the finished component, far beyond what you'd ever get by machining the same shape from a solid block of steel. Think of it this way. If you carve a wooden handle from a plank, you cut across the wood grain, but if you shape a branch by hand, following the grain, that handle is going to be much stronger. Radial forging does the same thing with steel. This process is used to make hollow steering columns for your car, drive shafts for heavy trucks, precision gun barrels for defense systems, aerospace landing gear components, and a whole range of fasteners and threaded rods. And compared to traditional cutting, where you'd waste a huge amount of material just removing metal chip by chip, radial forging is dramatically more cost-efficient. Less waste, less time, stronger parts. There are watches. And then there is the Patek Philippe Grandmaster Chime reference 5175. If you're the kind of person who appreciates things built to last, things made with patience, with pride, with an almost unreasonable level of dedication, then what you're about to see is going to stop you in your tracks. This watch was created in 2014 to celebrate Patek Philippe's 175th anniversary. Only 7 pieces were ever made. The price? Around $2.6 million each. But once you understand what goes into building one, you might actually think that's a fair price. The movement, a mechanical universe. At the heart of the Grandmaster Chime beats the caliber GSAL 3675 O'Keys Fus IRM, a movement containing 366 components, all assembled by hand inside Patek Philippe's manufactory in Geneva, Switzerland. Let that number sink in. 1. 366 individual parts, springs thinner than a human hair, gears barely visible to the naked eye. Each one crafted, finished, and fitted by a master watchmaker whose training alone took years. This movement powers 20 complications, that's horological language for features. Most luxury watches celebrate having 3 or 4. The Grandmaster Chime has 20. Among them, a grand sonnerie, a petite sonnerie, a minute repeater, an alarm, a perpetual calendar, a second time zone, and a 4-digit year display, among others. The Grand Sonnerie alone, the mechanism that chimes the hours and quarter hours automatically, requires a series of precisely tuned steel gongs and hammers that must produce a tone as clear and resonant as a Swiss church bell. Getting that sound right can take a watchmaker weeks of adjustment. The case, art you can hold in your hand. The Ref 5175 features a double-faced case crafted from 18-karat rose gold. But this isn't just a pretty shell. Both sides of the watch are fully functional dials, meaning you're essentially holding 2 watches in one. The front dial shows the time, a perpetual calendar with moon phase, and the second time zone. Flip it over, and the back dial reveals the striking mechanism controls, the alarm, and additional calendar indications. The case itself goes through dozens of stages of hand finishing, alternating between polished mirror surfaces and finely brushed satin textures, a technique called anglage on the beveled edges. Under a loupe, the finishing work looks like it belongs in a fine art museum. The dial, painted in time. The dials of the Grandmaster Chime are crafted using cloisonné enamel, an ancient decorative art form that dates back to the Byzantine Empire over 1,000 years ago. Thin gold wires are bent and placed by hand to create the design outlines. Then layers of powdered glass enamel are applied and fired in a kiln one color at a time, at temperatures around 800 degrees Celsius. This process is repeated multiple times, sometimes over 10 firings, until the colors achieve the depth and luminosity that Patek Philippe demands. One small crack, one imperfect firing, and the entire dial is discarded. Assembly, where time stands still. Assembly of the Grandmaster Chime takes place in a temperature-controlled room where even the slightest vibration can displace a component smaller than a grain of sand. Master watchmakers work under powerful magnification, using tools so delicate they feel more like surgical instruments than workshop gear. Each complication is built and tested as an independent module before being integrated into the complete movement. The final timing regulation, ensuring the watch keeps accurate time to within just seconds per day, can alone require several weeks of meticulous adjustment. Before any Patek Philippe leaves the manufactory, it passes the Patek Philippe seal, the manufacturer's own standard, which goes beyond the official Swiss chronometer certification. It's the watchmaking equivalent of signing your name on a masterpiece. This is the Goering RF100. Goering is a German cutting tool manufacturer with over 120 years of history, founded in 1898 in Albstadt, Germany. Every tool they make is engineered with obsessive precision, and the RF100 series is the crown jewel of their solid carbide end mill lineup. The RF100 is a solid carbide end mill with a very specific geometry that Goering spent years perfecting. Let's break down what makes it different. First, the flute design. The RF100 features variable helix flute geometry, meaning each flute has a slightly different spiral angle. That might sound like a small detail, but it's a big deal. Uniform flute angles can create harmonic vibrations during cutting, that chatter you sometimes hear in a machine shop that makes a part's surface look rippled instead of smooth. Second, the carbide substrate. Goering uses an ultra-fine grain tungsten carbide with a proprietary coating. They're fire coating, which combines extreme hardness at the cutting edge with heat resistance up to 200 degrees Fahrenheit. That lets this cutter run at feed rates and spindle speeds that would destroy a lesser tool. Third, the corner radius. Many RF100 variants feature a subtle corner radius, not a sharp 90-degree edge, but a small, precisely controlled rounded corner. That one feature significantly increases tool life, because sharp corners are where end mills tend to chip first. Watch how the tool moves through the material: steel, aluminum, titanium, whatever the job calls for. The cut is smooth, confident. There's no hesitation, no chatter. Chips fly off cleanly, and the surface left behind has a beautiful, almost mirror-like finish. The RF100 is available in diameters from as small as 1 mm all the way up to 20 mm, with a range of lengths, flute counts, and coatings to match virtually any material or application.